we're very happy to have Prerona Chatterjee talking about new lower bounds against homogeneous non-commutative circuits.
Okay, yeah, thanks. I'll be talking about lower bounds again in the algebraic setting, but this is in a different restricted model. So, yeah, Dipanshu has already told what algebraic circuits are, but quick reminder. So, they are directed acyclic graphs where the leaves are labeled by either variables or constants from the fields, and then every internal node is labeled by either addition or multiplication, and therefore compute polynomials in the most natural way. For example, one can check that this is the polynomial being computed by this circuit. Okay, and again, as Dipanshu mentioned, we want to study polynomials over n variables of degree d, and the major question is to give lower bounds for lower bounds against algebraic circuits or algebraic formulas computing some explicit polynomial over n variable of degree d, right. So, the central question is to find explicit polynomials that cannot be computed efficiently. And even though, as Dipanshu mentioned, there have been a lot of work which gives excellent lower bounds against constant depth or other restricted models of algebraic circuits, it turns out that in the general case, so the best in the for like general algebraic circuits, the best lower bound is quite weak. It was given by Bauer-Strassen from like 70s, 80s, which is just an n log d lower bound, so slightly better than the Boolean setting, but still quite bad. Okay, and so we want to. So this is the question we are studying, but again, we don't know how to do it in the general setting, so we want to look at some restricted some restrictions. Yeah. So the restriction we are going to be talking about is the non-commutative setting. Okay, so what is that? In this setting, the x, y, and so again we are computing polynomials syntactically, but in the non-commutative setting, the polynomial xy and the polynomial yx are not the same. So you cannot be reducing this thing to just x square plus 2xy plus y square. So what are non-commutative circuits? They are the same as general algebraic circuits, except that now the multiplication gate has to respect order, right? So yeah, that's it. So clearly the model is more restrictive, so you would expect that you should be able to give better lower bounds, and that's the question: can we do something better in this setting? And unfortunately, can we do? And it's reasonable to ask because there are actually like results which like very good results that we know in the non-commutative setting that we don't know in the commutative setting. So, for example, a major question is to separate. So, as Dipanshu was saying, they had constructed this polynomial first in set multilinear VP, and also he said that also a polynomial in set multilinear VVP, which is even better because we know that VVP is a subclass of VP, and it is an important question to know if the two classes are separate. We don't know in the general setting, but in the non-commutative setting, we actually do know a separation, an exponential separation due to Nissan. So similarly, again, the follow-up work that Dipanshu was talking about, that gives a separation between formulas and ABPs in the non-commutative homogeneous setting. Again, not known in the general setting, but we do know. And another thing is this lower amplification of lower bound. So the result of Carmosino, Impagliazzo, Lovett, and Mihalin show that if you can give superlinear lower bounds against constant degree n variate polynomials, then you can actually get exponential lower bounds against n degree n and n variate polynomials. Okay, so these are some examples of results that are known in the non-commutative setting, not in the general setting. So it's not unreasonable to ask whether we can give better lower bounds in this setting. But unfortunately, even in the non-commutative setting, general lower bounds, we couldn't give anything better than, we couldn't improve the one by Bauer-Strassen, maybe because of such like strong amplification type results that are known. But anyway, so the next question was, let's put another restriction of homogeneity. So let's assume that we are working against homogeneous non-commutative settings, and then can we do anything better? And in this setting, it turned out that we can do something. So we showed that any homogeneous non-commutative setting computing this ordered version of the elementary symmetric polynomial. So what is the elementary symmetric polynomial? You are just picking up d variables out of the n variables and just summing up all those monomials. We look at the ordered version because we are in the non-commutative setting, and we show that any homogeneous non-commutative circuit computing this polynomial must have size nd. For d smaller, for larger d, you lose a factor of log d, but yeah, essentially nd. Okay, and additionally, this bound is actually tight for in the homogeneous setting, and interestingly, you actually have a better upper bound if you don't put the homogeneity restriction. So additionally, our lower bound also gives us superlinear separation between homogeneous and non-homogeneous non-commutative circuits. Okay, so I'll now talk about how we go about proving it. It's actually surprisingly simple, which is why we believe that we should be able to improve it. But yeah, unfortunately, it would be very good if we can. Okay, so what is our measure? So suppose we are given a homogeneous non-commutative polynomial of degree d. What we do is we look at, for every position I, so from 0 to d, we consider this polynomial fi, which we get from f by setting variables in positions apart from I and I plus 1 to 1. Okay, so for every f and every position 0 through d, we will just keep the position I and I plus 1 alive and set other things to 0. So for example, if f was x1 through xd plus xd through x1, then f of 1 is x1, x2 coming from the first monomial, because you will have x1 and x2 in the first two positions, plus xd and xd minus 1, because the first two position is d and d minus 1. So it's not like we are setting variables to something, we look at positions and set things. Okay, and now that we've defined fi, what we'll do is the measure for a polynomial is going to be, you look at the span of all these fi's and look at the dimension of this space spanned by it. That's the measure. And the main observation is that for any f that is computable by a homogeneous non-commutative circuit of size s, this measure is at most s plus 1. Okay. So we'll basically be seeing a proof of why this is true. So, and we'll use it to prove. Okay, so I've defined what the measure is for a polynomial. Now for a circuit, you will do the same thing, but across all polynomials that are computed across any gate in the circuit. That's the measure for a circuit. Okay, and we want to say that for any circuit which is a homogeneous non-commutative circuit, the mu of c is at most the size. Okay, so and the idea is using induction. So for G1 and G2, because it's a linear span, nothing changes when there is a plus gate, right? So yeah, so there's no change in the measure at all. But at a multiplication gate, that's the non-trivial part. So suppose so you have G1 and G2 which are being computed at the children. Then for G1 you will have G0 to GD minus D1, and this is from 0 to D2. So now what is going to happen at the multiplication gate? So note that G0 is essentially just G10, and so on. GD minus 1 is G1D minus 1, okay? And then again 1 is going to become, G2 1 is going to be GD1 plus 1, and G2 D2 is this last term. The only thing that is not either in the bucket which belongs to G1 or in the bucket which belongs to G2 is this GD1, okay, because that is exactly the break point between the two children. And what is GD1? It's exactly the last monomial, the last thing that appears in G1 times the first thing that appears in G2. So the only new thing that is there in the span is that can be added to the span is this GD1, which comes from the product of these two. So essentially what this is showing is that for a sum gate, there is nothing that is added to this span which is there, this linear space that is there. And for a multiplication gate, there can be at most one additional element that is added to the space, which is why the rank or the dimension can increase by at most one in every multiplication gate, which tells you what, that the measure can be at most the size plus. In fact, it's at most the number of multiplication gates plus 1. And so so clearly, if Fc is the polynomial computed at the root of the circuit, then its measure is at most the measure of the circuit. And now if f is, for example, just x1 through xn, then mu of f is n plus, it's easy to see that mu of f is n plus 1 because you have all possible x1, x2, x2, x3 and so on. And using the earlier thing, you get that mu of Cf is at least n. Now the point is that, so what does this say? It says that any homogeneous non-commutative circuit computing x1 through xn must have size n. Now that is obviously true because there are n variables and you have to see all the variables. But the point is that just this simple idea can be used to prove something that is not so trivial. So now instead of looking at n variate polynomials, we'll just look at bivariate polynomials, so just x0 and x1. But now you have degree d. Okay, so now there's nothing, so it's just two variables. So all you know is that you have to see that has to be two leaves. And because it's degree d and it's a circuit, so the trivial lower bound is log d essentially. But we can use our previous thing to prove a d by log d lower bound. Why? Because what we say is that, so how do we change it slightly? We say that we change the measure from keeping just two positions alive to keeping log d positions alive. Okay, and now in this case what we get is that the measure is at most s times log d instead of just s. And now if we can find a monomial over a bivariate monomial of degree d such that it has measure d, then we would get our d by log d lower bound. And there exists essentially there exists such a monomial, and that monomial comes from the de Bruijn sequence. So what is a de Bruijn sequence? These are sequences over the 0-1 alphabet, such that every string of length log d occurs exactly once as a substring. Okay, and it turns out that there is a length d de Bruijn sequence of order log d, which means, so it's what this is saying is that essentially there are monomials in which of length d such that every log d length words appear in it exactly once as substrings. Okay, so now just look at the monomial which corresponds to this de Bruijn sequence, and you will get that its measure is omega d, and we have our lower bound. Now the question is that, we are now just computing a monomial. Why do we now additionally need this condition of homogeneity, right? Like, how can, and you're just computing one monomial, what can addition gates give you? What extra power is addition gates going to give you, right? That's the intuition now, but the point is that, so if there were no addition gates, if it's just multiplication gates, then obviously the circuit is homogeneous. But And now just when you are computing just a monomial, why should you need addition gates? We don't know, but unfortunately we can't even prove that addition gates is not going to give you any power. So the question is, and we strongly believe that we should be able to do this. We want to show that the same lower bound even holds against a general non-commutative circuit. And yeah, we are still thinking about it, and unfortunately we don't have anything yet. Okay, so this is for a single monomial. Now what I promised you is an ND lower bound against this ordered version of the symmetric polynomial. So the way we get to that is by using this result of Bauer and Strassen. What do they show? They show that if there is a circuit computing a polynomial then of size s, then there is also a circuit of size at most 5s that simultaneously compute all their partial derivatives. Okay, and okay, so now the point is we want to use that because this in some sense is going to give you an additional n factor in the lower bound. So what we have, I mean, yeah, what we want to do is say that such a result even holds in the homogeneous non-commutative setting. So Bauer-Strassen as it is doesn't, it's for general circuits commutative setting. And secondly, we want there to be an n-varied degree T polynomial f such that the measure of all its partial derivatives simultaneously is actually ND, and if we could do that, then we can combine it to give our load. And yeah, so now it turns out that a similar result is indeed true. We can show that a similar thing holds in the homogeneous non-commutative setting. And secondly, we want the other part, so that we need an n-varied degree T polynomial so that this happens. Now note that for this slight variation of what we did earlier already almost has this property, except that we are going to lose a factor of log d by the same reason that we had a d by log d for de Bruijn sequences. So now we don't want to lose a factor of log d, so what do is we realize that for this polynomial we don't have to lose the factor of log d. We have that if f is this ordered symmetric polynomial, then the first order partial derivatives measure is actually omega n d. Okay, so I won't be showing this part because this is easy to check. I'll just quickly go over how we changed the Bauer-Strassen proof to make it work for the homogeneous non-commutative setting. Okay. So let's just quickly go over the Bauer-Strassen proof, which is quite amazing actually. So what we do is that what they show is it's again by induction on the size of the circuit. So what they do is that you look at the first gate from the bottom, which has both children as leaves, and then if this was an addition or a multiplication gate, both case what you would do is you would replace this sub-circuit of just a product or sum with two leaves to be a new vertex V, and then what you would do is you assume by induction, because the size has decreased, so the number of edges have decreased, you assume that this can compute all the partial derivatives simultaneously with a blow up of only 5s, and then you assume then you use the chain rule to reconstruct the derivatives with just respect to x1 and through xn to get back the thing. Okay, so for addition, yeah, so essentially it's just reduce the number of vertices or edges, assume by induction that you can compute all the partial derivatives simultaneously, use chain rule, and to get back our original thing. Okay, so now the problem, and it turns out that it all works out. Now the problem is just that the only thing we needed to take care of is that because we need this homogeneity condition, now just assume that above this multiplication gate there was a sum gate, okay? And now when we did this has become a degree 1 node, whereas because we assumed that the original thing was homogeneous, the other child over here would have had a degree 2 node. Okay? So now when we did induction, we have lost homogeneity. So what we need to make sure is that the circuit somehow remembers what its original degree was. Okay? And the way we do that is by keeping track of that original degree, essentially by this notion of weights. Okay, so we define W homogeneous to be a circuit which is homogeneous with respect to these weights instead of just degree. And we show that Bauer-Strassen's result continues to hold using the concept of W homogeneous instead of just general circuits. Okay, so we have W1, W2. We for a sum gate, of course, because by induction it's W homogeneous, so it will be the same weight. For multiplication gate, each time we collapse, we put the weight of W1 plus W2 instead. Okay, and essentially it just works out. I don't want to go more into it. And also, because we are working in the non-commutative setting, we need to define formal derivatives. So, so we just have f equal to x times f0 plus f1, where f1 doesn't contain x in the first position. And then the derivative with respect to x will just be f0. And again, everything goes through. Okay, and upper bounds, as I mentioned, there is a homogeneous non-commutative circuit. So this shows that our lower bound is tight. And if you don't have the homogeneous condition, you actually have a better lower bound of n log square n. This is again, I mean, it's easy to, I mean, it's interpolation essentially plus FFT if you know, like it's a base. I mean, it's nothing non-trivial if you already know the literature. Okay, and this, but interestingly, this what it does show is a superlinear separation between homogeneous and non-homogeneous non-commutative circuits. Okay, I guess the most interesting thing is how our result fits into if given the results of CILM. So let me just once more go over the results. This one I had mentioned earlier, which is that if you have a superlinear lower bound for an n-variate constant degree polynomial, then that implies an exponential lower bound. Okay, but our polynomial, even though it's a superlinear lower bound, it's not a constant degree. So this result doesn't kick in. Now they also actually have a different result which says that superlinear lower bounds, so of the type n to the omega by 2 plus epsilon, for n-variate degree poly n polynomials would imply arbitrarily good polynomial lower bounds. Okay, so now here it seems like we have superlinear lower bounds and it is for a degree n polynomial, so it should kick in to give this. And it actually does, but the point is that it's a bit subtle, is that, so let's just go over what exactly this result gives. Okay, so what they do is they start with an capital N variate small d degree polynomial and assume that, so here I am just assuming omega is 2 and keeping it as n to the 1 plus epsilon. Okay, so they say that if you can give such a lower bound for capital N variate small d degree polynomial, then they will give you n to the arbitrarily good. So think of c as a large constant and epsilon as a small constant. Okay, by changing the number of variables, as you can imagine, the number of variables will reduce and the degree will increase. Okay, that's how CILM's proof works. And now what are exactly the variables? The variable will actually be capital N to the epsilon by c. So epsilon is small, c is large, so number of variables is decreasing and d becomes c by epsilon times d. So it's increasing the degree. And what this S prime actually just looks like capital N to the epsilon. So if you had given n to the 1 plus epsilon, the new lower bound is n to the epsilon. Okay, and this is now n to the epsilon looks like small n to the c, and that's what this is. Now let's just look at what our result plus CILM does. So our result is capital N d, okay, which means n to the epsilon is just d. Okay, so what does that mean? S prime is just small d, and that so our so CILM the lower bound it will give is just small d, whereas our lower bound on n comma capital D, which is the right hand side of this arrow, that is again capital n times capital D, which is actually much better than just D. Okay, so which is why we didn't like say it this way separately, because our result plus CILM bootstrapping is not giving something as good as what our result anyway gives. Okay. Yeah, I think that's all I want to say. Open questions, I think I've already mentioned. We want to give a D lower bound for general circuits and also an ND lower bound for constant variate. Yeah, we couldn't prove it for a constant variate, so it would be nice to prove it for constant variate. As we couldn't do it because we didn't have a Bauer-Strassen version for a constant. Yeah, that's it.
Thank you very much. Questions? Well, I do have a question, though. So when you go to the non-commutative setting, then homogeneous polynomials are the same as tensors.
Yes.
Right? And there's a extensive literature on tensors, and there even people have studied circuits on tensors also.
Mm-hmm.
Have you looked at the connections there?
Not too much. I mean, yeah, I'm not. No, actually, not too much. Yes. Okay. I should. Yes.